Welcome to the first video of NoSQL database series. In this video, we'll be discussing the important topics of first module. So there are three chapters in first module, right from the intro part, that is chapter 1. Then we have the details about the aggregate database models, data models, that is the second chapter. And third chapter is in details about what data models are and what are the types of data models. So do check out the NoSQL playlist. I'll try uploading all the module-wise videos, and important question video is also uploaded. So do check that out. And if you're new to my channel, do subscribe so that you don't miss out any of the updates. Now let's get started. The first topic which we'll encounter is about the value of relational databases. So in the first chapter, it's all about discussing what is the conventional database and what are the differences, and or how is the new NoSQL database better than the conventional databases. So first chapter deals with all these topics. So the first topic is value of relational databases. That is, what is the impact or the importance that the relational database hold in the actual market. So the first point is getting at persistent data. Persistent data means something like it is like a permanent data that is stored on a storage medium. So it is like a long lasting data which can be retained for a long term purpose or long term use. So database should be able to store large amounts of persistent data. So this is one of the basic characteristics of database, right? That is, it has to store large amount of data irrespective of the system or its compatibility. So most computers have two sorts of memories or two sorts of storage compartments. First one is main memory, and then we have is the back memory. So main memory is fast, but it is volatile and it is limited. Whereas speaking about the backing store, it is usually a disk or other persistent memory. So it is large, slow, usually disk. And one more example is file system. So main memory is just limited in space and it loses the data when we shut down the system. So this is one of the drawbacks of main memory. So database allows flexibility than compared to the file structures in storing large amount of data in a way that it allows application program to get at small bits of that info quickly and easily. So when you're storing the data in your memory, and on the front end you're writing some program to retrieve this data, it has to happen over a quick time, right? So it should not take a large amount of time, and not just that, even the processing should happen quickly. So that is one thing. So by making use of relational databases, it provides a persistent data storage and data retrieval procedure. Next we have is concurrency. So in enterprise applications, multiple users may access the same data at once, right? So thereby, like suppose let me write down here. Suppose I have an account named savings, and two people have the authority. Username and password are being shared by two people. A is adding 100 rupees and B is deducting 500 rupees from the account. So when A is adding 100 rupees, the total would be x plus 100, and when B is deducting it, it would be x minus 400, x minus 500. So if both the operations are done together, there will be data loss, right? So there will be inconsistencies which will occur here. So multiple people are trying to access the data at once. So modify the data at once. If you are not handling it properly, it could lead to problems. Like suppose the bank account example which I told. So in order to overcome this, relational database will handle by controlling the access to that data through transactions. So transactions is the basic concept which we have studied, which is used to overcome the concurrency issues. Right, transaction is very important for error handling, and it significantly reduces the complexity, and it will help to manage the concurrency effectively. So again, concurrency is one of the important topics under value of relational databases. Next we have is integration. So transactions in relational databases will also have error handling, right? So when a change is made, there could be an error which is occurring during the processing. So either the transaction could be rolled back or it could undo the change which is going on. So this is very important in case of enterprise ecosystems where multiple applications are being developed by different teams, and all these teams need to collaborate all the data and work together. So multiple people are writing multiple changes over the data, all should be combined. So there has to be one application which is visible to all others, or one platform which is accessible to all others, and thereby they can do required changes. So here we have shared database integration. So shared database integration is a common approach where all the applications will store and access the data under one database. So here examples are Hope. So this was introduced by this person, Hope and Wolf. So he was a person, they were the ones who introduced this concept of shared database integration. So by making use of this, it will simplify the process of data sharing, and the database built-in concurrency control will also happen here, and even the error handling also happens carefully. So we are storing the data in a single database here. Next we have is a mostly standard model. So can we say that relational database is the standard model? Yes, it is mostly a standard model. We could say 98% it has been widely used, right? So one of the reasons why the relational database have remained consistent in this market is because of the features which they offer, because of the benefits which they offer. So the relational databases succeeded over the market. Be it the developers or the database administrators, they can learn easily because the core concepts are universal. Ease of learning and adaptability is also very easy. And not just that, along with the other applications also, it is very simple to integrate, as well as similarities across the vendors will make like different SQL dialects could be there. So all these fundamental mechanisms remain consistent. So thereby, this standardization makes our relational database widely accessible and usable across various environments. So this question could be asked for 10 marks, and you have to explain all these 4 points with proper examples as and when it's required. Here we have to mention an example. Here there's a necessary of mentioning an example and specifying it. Next topic which we have is impedance mismatch. So impedance mismatch is one of the drawbacks which occur in the relational database. So impedance mismatch could be asked for 10 marks because it is a very important topic in first module. So difference impedance mismatch is the difference between the relational database model used by the database, which comprises of tables and rows, and the rich in memory data structures, which comprises of the objects, list, nested resources, nested records, and which are these rich in memory data structures are used in the programming languages, right? So when there's a difference between the conventional database model and the rich in memory data structure, it is called as impedance mismatch. Mismatch means there's a difference in there is a difference between two things. First one is the relational database, like we have seen tables, rows, columns, all those things, and on the other hand we have the complex data structures here, which could be objects, lists, or nested records, and all of that. We'll look into these one by one. Okay, so speaking from the relational database model, so relational database offers many benefits. We know that. Along with that, there are also shortcomings. That is, database is organized in tables with rows. Rows are called as tuples. We know tuple is relational model which comprises of set of simple names or value pairs. So relational data model lacks support for rich data storage directly. So there is a difference, like relational data model cannot store all these complex data structures, all these rich in memory data structures, right? For example, a order containing multiple items, like there could be a nested list here, can't be directly stored as single entity in the relational data model. So we cannot store it, and the simplicity of relational tuples come with a limitation. That is, these tuples are very easy to access, simple to handle, but they cannot include the complex structures. That's what we have discussed here. When in contrast to the memory data structures, in memory data structures which are used in programming languages, they comprise of far more complex things, and they have rich hierarchies and nested collections of data, right? And they are supported by Python, Java, C++. They are complex and flexible. They allow nesting, and they have more expressive representation compared to the relational model. So you can see one is the very classic simple thing, and on the other hand, we have a complex and rich hierarchy, or a difficult, or let's say an advanced version of data storage. So when developers want to store this in-memory data structure or complex in-memory data in the relational database, they will have to first translate it into flat and tabular structure of relational database, tabular format. So this process is difficult, and it could lead to inefficiency, bugs, and frustration. So it will increase the complexity in memory mappings. So this translation process of conversion from memory in memory data structures to the relational model, or converting it into flat structure, is called as impedance mismatch. So if you consider this figure, it is an example where application has a order. So you can see this application has an order. So we have ID, customer name, what are the line items here, and what are the payment details have been specified here. So it like this is specified in the user interface, and it is represented as a single aggregate structure which comprises of all these things. Right. So when we are storing this in the relational database, the data need to be split into multiple tables and rows. Like there could be separate tables for items only, right? There could be separate tables for customers only, and there could be separate tables for expiry, credit card. If there's shipping, also separate table could be there. A single logical entity, right, which comprises of all the order details. So you are splitting this, or you are fragmenting this single logical entity into many rows which are across different tables. So there are different tables here. So by doing this, it will highlight the complexity of memory mapping or memory mapping in memory structures to relational data stores. So this is an example where impedance mismatch will occur. Next, we have the object-oriented challenge. That is, during rise of object-oriented mapping in 1990s, object-oriented database aimed to eliminate the impedance mismatch by storing objects directly. But relational database stopped this due to these are the following reasons. First one is SQL standardization. SQL standardization means SQL, that is the standard query language for the relational database, became widely accepted, and it was accepted by all the vendors. Multiple companies were using it across different database systems, right? So this standardization helped the developers as well as the database administrators to communicate or perform the operations with a consistent language for managing the data. That's why when you're trying from past 10 years, you're following a habit and suddenly someone tells you to shift that, it'll be difficult, right? So SQL standardization was one thing which stopped this conversion process. Next, we have integration rule. That is, relational database focus their role in integrating multiple applications by serving as a central data repository, right? So it will enable various systems to share and access the same data. So if you are opting for object-oriented database, there might be variations. That's when even this was the reason why it stopped. Next, we have professional separation between the developers and administrations. The growing distinction between the application development and database management led to emergence of specific roles like application developer, which was focused about the business logic. Then we had database administrators, which was about the data storage and optimization, specialization, and all those things. So these were the reasons which stopped from the conversion to object-oriented database. So if they ask about impedance mismatch, you have to explain what relational model is, what in-memory data structures are, draw this figure, and then explain what each and every table means and how does it speak about the impedance mismatch. Then also include these points. Okay, that is what is the object-oriented challenge, and what are the points which stopped from the application of the object-oriented database. Next we have is application and integration databases. So under this first one we have is integration database. Integration database means it is the shared database which is used by multiple applications. So multiple applications are sharing the same data. Further, all this data is being integrated into one. That is, separate teams will be there. All these separate teams would be sharing different data, right? Different database. So integration database will act as a common integration which will ensure consistent and persistent data storage. That is, when you're integrating all these different chunks of data into one and storing it as a company's database, that's what is called as integration database. So here this might be the record of 7A, 7B, 7C, 7D, and 7E. When you're storing it all together, it is class 7th sem, right? Here it was all about the sections, different sections, or it was about sections, and here it could be about the department, that is ISC. Like this is just an example. Okay, so advantages here were the simplified communication. So when you're combining all the different tables, the communication becomes very simple. You can easily communicate or transfer the data. Not just that, there was single source of truth. That is, when you have to fetch the data, it has to come from one source. This one source, when you're combining it into one, when you're combining multiple data into one source, it becomes very easy to retrieve the data, right? So thereby these were the advantages. Speaking of the disadvantages, speaking about the disadvantages, first one was complex schema. Complex schema means it is see, we have integration database which is designed to cater multiple applications. So there might be complex like complex structures that any single application requires. At that case, it will become very difficult to handle, right? Then we have coordination issues. That is, changes to the database schema or the indexes need to be addressed or agreed with all the other databases which are present inside my big database or the integrated database, right? So this can lead to delays or conflicts. Thereby, coordination issues were also a thing. Next, we have is performance conflict. That is optimization. If you're trying to optimize one application, it might impact the other application also, or it might slow down the other application, right? So thereby performance conflict could also happen. Next, where is data integrity? Because we are integrating multiple teams across the database, it has to follow the integrity rules properly. So proper obeying of integrity rules should happen. If not, the data might get lost. So if this particular database is not following the rules properly and the rest three of them are integrated, then this data is completely lost, right? So thereby, all these were the advantages and disadvantages of integration database. Next we have is application database. Application database is a database which is designed for single application and it is managed by a single team or a single development team. Looking at the advantages, it is very simple to handle. Like only the application team needs to understand what is happening or what is the data structure, what is the database structure. So thereby, if you have to update also, no, it is very easy here. Next we have is better flexibility. That is, teams have full control over the database. They can make any changes whichever they want, and they need not refer to a third party also or external resource, external coordinator. Nothing is required. Then we have data integrity in code. That is, data integrity in code means the responsibility for maintaining the data integrity is shifted to application code rather than the database. Next, we have custom data structures. So decoupling from the integration, that is breaking out from the integration, allows the use of non-relational databases or rich data structures. It could be the XML or JSON format for application specific needs. So all these were the advantages. So communication using HTTP web services. So applications will communicate by making use of web services like HTTP instead of directly communicating or directly accessing a shared database. So by doing this, it will enable a richer exchange of data with the nested structures, and it will also reduce the number of rounds which are required in the communication process. Speaking about the disadvantage, we have high performance needs. That is, for performance sensitive interactions like binary protocols might be required, or text based protocols could be required. So all these are certain little difficult to handle, right? So this was the disadvantage or drawback or the challenge about application database. So both of these could be asked for 5 marks. You just have to mention these points elaborated, and yeah, that's it. Next we have attack of clusters. So attack of clusters, in early 2000s there was a rise in the web properties handling large scale data from links, social networks, and mapping data. So as the amount of data was increasing, the data traffic was also increasing, and thereby the companies were facing a scaling issue or scaling challenges for scaling their computing resources. So there were two solutions, or there were two ways to scale. First one was scaling up. Scaling up means you're adding more power to one machine. It is you're installing a new processor or adding a new memory component or anything like that. Then we have scale out. Scale out means you're using smaller machines. Smaller machines could be in form of clusters. This option was cheap and it was more resilient, and it could handle individual machine failures without affecting the overall availability. So if one machine fails, it wouldn't impact the other machine because you're scaling out. It is all split into different clusters of tiny computing devices, right? So however, relational databases even struggled with the clusters also, right? They were designed for single server environments, and they could not handle the distributed data management well, right? So although we had sharding and other features, they did not help to distribute the load properly. There could be issues like losing the data, or like compared to referential integrity, sharding was not that impactful. So the relational databases could not integrate it properly, and that is what we faced as one of the major issues. So large scale companies like Google's Bigtable, and Amazon Dynamo, so they had a vast amount of data and they began to look for other alternatives. So they developed with the Google Bigtable and Dynamo. So these were the database models which worked well over clusters. So these models were a certain alternative to the drawbacks which we were facing with the relational databases. So these big table and dynamo were the basic foundation upon which NoSQL databases further developed. So next we have is explain the emergence of NoSQL database. So it could be asked for 10 marks. Again, it is very easy. So NoSQL or NoSQL was first used for relational database, and it was developed by Carlo Strozzi, which stored tables in ASCII files and used shell scripts for operation instead of the SQL queries. So this was in the initial origin of 1990s, and this version of NoSQL had minimum impact on the modern database trends. Next, we have the modern NoSQL movement, which was in 2009. So John Oscarson organized a meet to discuss non-relational database, which was inspired from the Big Table and Dynamo. We have discussed here about Big Table and Dynamo. So this meetup was about speaking about the non-relational databases, and the inspiration was taken from Big Table and Dynamo. So this is where the term NoSQL was suggested by Eric Evans for the event. So this basic NoSQL was for the event. It was to not to oppose SQL entirely, but to highlight the alternative approaches to data storage and management. So further, it got its name as NoSQL only. So speaking about the characteristics, first one is lack of resilience on SQL. So compared, first one is lack of resilience on SQL as a query language. Then we have focus on schemaless or flexible data structures which will support the non-uniform data. Next we have is the horizontal scalability. So NoSQL supports horizontal scalability. It will allow efficient operations to happen even in the distributed environments also. It is designed for the large scale data handling. Examples would be the web scale applications and all. Then it is open source, and it is community driven development, and it is accessible by everyone, right? So examples, further examples, we had MongoDB, Cassandra SQL. This is a closed source system, whereas MongoDB is a open source system. So in summary, we can say that NoSQL emerged as a response to challenges of handling large, diverse, and distributed data sets in modern applications, offering a scalable, flexible, and efficient alternatives to the traditional databases. So if they ask this for 5 marks, this much would be sufficient enough. And if they ask for 10 marks, here I have just mentioned 5 characteristics. Do mention at least 7 characteristics. So you can just write about the polyglot persistence, and what are the open source, closed source systems, what are the key drivers for adaptation of the NoSQL and all. So you can just mention points accordingly. Schemaless, and it was designed for 21st century web estates, all those things. Next topic we have, this is from the second chapter about the aggregate database models, aggregate data models. First topic we have is what are data models. So data models will tell us how we interact with the data in database as opposed to the storage model. Storage model will tell how the data is stored and manipulated, but data model will tell how are we interacting with the data that is present in the database. So data models are entity relationship diagrams in an application. So application example is the customers and orders. We'll look in, we saw it previously, right? So customers were there, orders were there, and all of that. So database organizes data in meta model. Okay, so developers refer data models as entity relationship diagrams in an application, but in the actual context, data model is referred to how the data is organized. It is also called as meta model. So speaking about the relational model is based on relations. Like it will have tables where each table will have rows or tuples, and that these tuples will represent the entities of that particular column. So column here describes the entities, and relationships between each other can be represented using the table. So table comprises of rows and columns. We know this. Speaking about the NoSQL databases are different from the relational data model. They won't have tables. So they have different approach of storing the data, organizing the data. That is, these are the approaches. First one is key value, then we have document, column family, and then graph database. So this was a tiny introduction about what data models are. We'll look into aggregates. Aggregate is a must question which could be asked for 10 marks. So we know then in relational data model, data is stored using tables which comprise of tables, which comprise of rows and columns. Right. So here each row will represent a record. So record, and each record will have a set of values for their attributes. So this is the basic thing which we have discussed. So there will be a table which will have certain rows, and each row will represent contents of certain columns. Right. So this is the brief introduction. So the key limitation here is that it does not support nesting. That is, we cannot store the lists, array, or any other complex data structures within a single tuple. So if you are trying to store within a single tuple under salary, if you are trying to store salary is integer, under this if you are trying to store the employee's name, his age, his email, his salary in a given table, is it possible? No, right? Because under salary it can store only one thing, that is the salary of that person. You cannot store the complete or the entire thing into one tuple, right? So this was one of the key limitations, that is relational database is based on the flat structure, right? So it cannot store complex data structures within a single tuple. So to overcome this, we came up with the aggregate orientation. So this was about the basic relational model, and then we have aggregate orientation, which recognizes the data is often manipulated in complex structures rather than simple tuples. So here we are storing the data in complex structures rather than storing in simple methods. So aggregate is a term that will aggregate allows nested records and lists, making it easier to treat relational data as a unit of operation. So when you are dealing with the relational data, entire thing could be taken as one unit or one entity, and it could be further processed. So that was one of the advantages of aggregates over the relational data model. Looking at the definition of aggregates, aggregate is a term that comes from domain driven design, that is DDD. It refers to a collection of related data that should be treated as a single unit. So domain driven design will tell that whatever data you are storing, this entire thing should be treated as one unit. Okay. So aggregates can include nested data structures as lists, records, or any other entities. So the common NoSQL databases that follow this are the key value stores, document stores, and column family stores. So aggregate comprises of a logical boundary that will have a set of data that is updated or retrieved together as one unit. So this is what I explained, right? So it makes easier to perform operations. So instead of performing operations on multiple different tables or different entities, when you club all those things as one and you're considering them as single unit, you can easily perform operations over the single unit, right? So the operations like sharding and replication become very easy here, or it becomes very easy to perform all the other operations, as they know which data should be kept together or stay together in a cluster. So this was about the basic introduction about the aggregates. So we have seen the different types, right? Before covering these topics, let's look into the example. So example is about relational versus aggregate model for building a e-commerce website. This e-commerce website will comprise of users, product catalogs, order shipping, and payment information. So this first figure 2.1, is the basic relational model, basic data model around relational database using the UML notation. So here we would use the normalized tables with the foreign keys to connect with each other, like customers, orders could be connected each other. Customer details and orders would be stored in a separate table with a foreign key which is helping to link with the orders to the customers. So it could be with address also. So here we'll come across normalization. So normalization is you're splitting the given table into multiple tables, right? You're doing this because to ensure that there is no redundant data happening. Along with that, referential integrity is also working because you're making use of foreign key here. So this is the basic relational model which we have. On the other hand, this is again a typical data which is you can see the data is being stored using the RDBMS data model. So you have order item here. So order ID would be there. Order ID is referred here. So this is the foreign key, right? So in exam, if they ask, first you should draw the relational model. This is not required. This is just for our understanding. After that, we have to come up with this aggregate data model. Aggregate data model provides a detailed understanding of how a single aggregate might represent a customer and all their orders together in one object. So you can see the entire thing is being represented in one object. So this is Similar to the JSON representation, if you see here, the code which we have written is in the JSON format. So for customers, all the customer details have been specified into one object. For orders, all the order details have been specified into one object. So customer aggregate will contain not only the customer's personal details but also array of their orders. It will also have details about the customer's orders, right? So each order will have the order items, shipping address, and payment details within it. Right, this model, if you see, is denormalized. Right, here you are trying to split one table into multiple tables, whereas here you are trying to combine multiple tables into one object. So this is denormalization is happening here. So this denormalization will reduce the necessary for complex joins. So we were using complex joins to deduce data from this relational table, but here you need not make use of complex joins. Because of that, the data retrieval will become very fast. Right. Here we have one more figure which has embed all objects for customers and the customer order. So this figure will suggest that the customer aggregate could contain all of customers orders as a part of same data structure. So here each customer record will have a list of all orders they have placed fully embedded with the customer's aggregate. So it will have all the customers, all the products, order items, payments, and all the details would be specified along with the address to the customers. Here it is further embedding, further you're encapsulating all the details here. So this approach is useful when there is most frequent interaction is happening all of customers orders at once. In such cases, we can come up with this application. Here we have um, here we have aggregate boundaries. So aggregate boundaries means, suppose you're taking customer and order, or customer data and order data have distinct aggregates, right? So you're drawing up boundaries or you're separating here. So you're separately encapsulating customer details in one object and order details in one object. So customer aggregate will contain all the details of customer including the billing address, and order aggregate will also contain the data related to order including items ordered, shipping address, and payment details. Next we have is data duplication. So here we are making use of JSON format, right? Suppose you can see in billing and shipping that the same data has been written here, right, in JSON format. So data duplication is also happening here, but this approach will allow us for immutability of certain information. For example, if I don't want the shipping address or the payment details to change after our order has placed, it can happen here, right? So instead of linking address by a ID or updating them globally, addresses are copied wherever they are needed. So both the situations can happen here. Next we have is aggregates and relationships. That is the link between aggregates. For example, the customer or the order. So the link between customer and aggregate is maintained through fields like customer ID. So when you write customer further, we'll have customer name and customer ID. And to connect with order, we have order and which customer has placed it, right? Customer ID will be there here also. That's how the link is established between these two, and it is maintained through fields like customer ID. So this shows the relationship, but it does not imply aggregation. So the customer and order aggregates are separate. They are two separate entities, right? So within the order also there will be product ID, right? So which is separate from the product aggregate. So here we are looking into denormalization process, so thereby reducing the need to access multiple aggregates. Next we have is aggregate design consideration. That is one of the main aspect here is trade-off. So trade-off is like whether I want to bundle the related data like customers and their details into single aggregate, or I want to keep it separate. So this choice will depend on me and how I access the data. So suppose if I'm trying, if I'm frequently accessing the data, then I can store it into one object. And if the details are like independent of each other, then it is better to keep them as separate aggregates. So that is about the aggregate design consideration. Next we have is consequences of aggregate orientation. Under consequences, first one we have is easier for clustering and sharding. So aggregates help database decide how to distribute the data across different nodes or different clusters. So here related data is grouped into aggregates, and database can place all parts of an aggregate, for example the customer data, their orders, details, and all those things into one node. So thereby it will improve the performance and minimize the inter-node communication to happen. So it is very easy for clustering and sharding process to happen. Next we have is transaction management. So we know relational databases will follow the ACID properties, whereas if you are speaking of NoSQL databases, it do not follow the ACID properties. It has only atomic transactions which will happen in a single aggregate, right? So if I need to manipulate multiple aggregates simultaneously, I'll have to handle all these in a application logic. So thereby transaction management is also happening properly. Next we have is performance and flexibility. Aggregates can simplify the application logic by focusing on the high level operations on the entire data set, right, rather than worrying about what is there in the single record or relation between the tables. Thereby, it can become problematic if the application needs to perform operations that span across many aggregates. For example, I want to analyze the product sales across many other orders. So this would require accessing many aggregates, right? So thereby it could be less efficient than the relational model where everything is stored in a normalized form and you are referring each other by making use of foreign keys. So this was about the aggregates, and if they ask about aggregates, you have to firstly define and what is the case of relational database, what is aggregate orientation, definition of aggregates, features of aggregates, and draw this diagram of the basic relational database model. And here we have the aggregate data model. Then you should specify the JSON format here, and here if this is not that required. Okay, so just draw this diagram and specify it properly here. So under customers we'll have ID, so customer ID something would be there, and then under customers what do we have? Name we have. So below name, below ID we have name something you write, and then billing address would be there. This billing address is further redirected to address here. So you put a square bracket here, open it, and then you fill all the necessary details of address here. Okay, so JSON format is very easy. I hope you have studied this. So next we have is key value stores. So key value stores are the databases which will follow aggregate oriented approach. So they'll follow aggregate model, that is combining multiple entities or multiple objects into one object and storing them together. So data or aggregate is opaque here, that is they are treated as single blob, that is binary large object. Okay, so it will allow complete freedom over what can be accessed or stored as database. So it only recognizes aggregate as blob. So here the key value stores, we are storing blob, binary large objects, and this entire thing whatever you are storing is recognized as one single unit. So we can access these using the key. So along with the key, there would be some value which was stored together with it. So by making use of this key, you can get the value whatever you want. So this simplicity provides flexibility in the data storage, but it limits how the data has to be queried. That is, query limitations are there here. Speaking about the document database, so document database will impose some structure on the aggregate. So it will tell aggregate, although you are storing entire thing as one unit, there has to be some structure which has to be followed. That is, it makes the query based on fields within the document. So here the entire thing is stored in a document format. So this will allow users to retrieve parts of an aggregate and even create indexes for quick recovery or for faster access. So it is powerful compared to the key value stores. So flexibility of document databases, if you are comparing, then it is slightly powerful in certain use cases compared to the key value stores. Next we have is, so either the document stores or key value stores or column family stores, their flexibility or their usability completely depends on where you are using it, where you are utilizing it, right? Next we have is column family stores. So column family database or column family stores examples are the Google's Bigtable and its derivatives like HBase, Cassandra, and all those things. So here column family will store or arrange the data in two-level aggregates. This two-level aggregates will have rows and columns. So these databases are used for storing and retrieving large data sets. So they are optimized here. So there are two approaches here, row oriented and column oriented. So each row can be seen as an aggregate, okay, in row oriented. So for example, column, and the column family will represent chunks of related data within that aggregate, like what is the customer profile, name, details, and all those things, and what is his order history, payment details, and all of that. Custom columns within a row can vary across different multiple rows. So column across one row can vary across different rows here, right? So thereby making these databases suitable for handling complex and diverse data structures. Next we have is wide and skinny rows. So wide rows means it will have many columns. Okay, so it will have many columns, and skinny rows means it will have few columns which are shared across multiple rows. Next we have is sorting and ordering. So column family databases allow for sorting columns within a family. So this will have efficient queries and the retrieving orders by a combination of date and ID. All such things can happen here because you're combining the multiple sorting columns within a family, right? Thereby the time series data or the application required for a particular large data set, all those things could be done easily or efficiently here. So this was about column family stores. Next we have is the graph database. Graph database could be asked for 10 marks. They'll ask you to draw a diagram. What are the features of graph database? And yeah, that's it. So understanding graph database now. So this is topic from third chapter of first module. So graph database is a unique approach. So unique approach within the NoSQL ecosystem which focuses on the complex relationships rather than the large aggregated oriented data models, oriented data design. So this graph database has emerged to overcome the limitations of relational databases, thereby focusing on small records within the complex interconnections. So graph will comprise of nodes which are further connected by edges. So we know graph will have nodes and edges, right? So they are used in social networks, product recommendations, and all those things. Suppose G wants to get details of A. So if G searches in, suppose this is a Twitter account, let's say, or a Facebook account. If G wants to retrieve a data of A, then G will search A in the search bar, right? So this data retrieval happens through a set of sequences or a set of patterns which goes. So G is employee of D and D is a friend of A, so thereby A details could be fetched that way. Okay, so it is used in complex connections, complex interconnections, which are examples could be seen in the social networks, product recommendations, and so on. Applications here are the FlockDB. So FlockDB will offer basic nodes and edges without any additional attributes. Then we have is Neo4j. Neo4j will allow properties to be attached to the nodes and edges in a schemaless manner. Then we have Infinite Graph. Infinite Graph is used to store the Java objects, right? Yeah, this was about the applications. So graph database makes use of specialized query operations that are based on structural relationships. So if you want to query the graph databases, you will have to come up with the specialized query operations through which you can get the details. So if you are comparing at the relational databases, you will make use of foreign keys, right, to get the details. So there it is very costly because you are using join operations, it is time consuming. But then speaking about the graph database, it will have cheap traversals across the relationships. So this efficiency is achieved by shifting the burden of relationship navigation from query time to insert time, and along with that you are also making the queries much faster in scenarios where you are prioritizing the querying over inserting data. So most queries here will navigate through network of edges. We have seen how the navigation actually works. So but we need a start point. So definitely we need a start point to start querying, right? So if you speak about the differences from the aggregate oriented models, aggregate oriented databases, in terms of architecture, graph databases will run in single server, whereas in whereas compared to the aggregate oriented models, it will run in the distributed clusters. Then we have asset transactions. So maintaining the consistency in graph databases requires transactions that span across multiple nodes and edges. Whereas if you see in the aggregate oriented databases, it will focus on a individual aggregate or individual object, right? So these are the differences between the aggregate oriented model. Next topic which we have is schemaless database. So schemaless database means it is schemaless, that is it has flexible nature, it is flexibility, and it is dynamic approach for saving the data or storing the data. So in normal database we are having a predefined schema, that is you will specify what the table should have, and in this table if you are specifying salary should be integer only, and how many integers should be there, or if you are specifying USN should be varchar of 10 elements only. So you are specifying all the details here. You're structuring all the schema here. But then speaking of the schemaless databases, that is in the NoSQL, it is not required here. So thereby it will provide a dynamic approach, flexible approach to store the data. So in schemaless databases, we have key value stores, that is I can store any data under any key without any restriction. I can store photos also, videos also, and documents also under one database. Next I have document database. So documents can have varied structures and there are no restrictions to the content which is stored in this document database. Next I have is column family. So I can store different types under any column. Now in salary it is not specified that I should store only the integer value, I can store any value. Next I have graph database. So in graph database I can add the nodes, how many ever nodes I want, I can add the edges and I can adapt the structure as in how I need. So this enables modification. So schemaless databases enable modification of data storage as required changes. So it is very useful for evolving projects. So when you're dealing with the evolving projects, so when the database or when the data requirements change after a certain point, if you're using the normal data structures or the normal conventional data model, it will become difficult. So suppose you're in the storage, they have told we have only 4 features, and suddenly in the middle, if I've completed 50% of the job, they are telling me that instead of 4, make it as 10 features something. So thereby the data storage has increased here. So in such cases I can go up with schemaless database, thereby it is very easy for modifying the data storage. Schemaless databases will also handle the non-uniform data properly, whereas in the relational databases it doesn't happen only, right? We'll look into the challenges now. So what are the challenges and problems of schemaless databases? So first one is implicit schemas. So implicit schemas in application code means even though the database is schemaless, application code itself will impose a implicit schema. That is program, it means program accessing the database expects certain field name and data types must be treated as specific type or structure. Suppose if I am storing salary only, then it is expected that under salary I will be storing only numeric data. I am not specifying the length of this number or integer data. I am not specifying the length, but then under salary I should store number only. It is expected from the database itself. So it becomes difficult to read as the data is hard coded in application code. So the implicit schema is hard coded in application code, that is it will be difficult to understand the structure of data, requiring to read and interpret the application code itself. Suppose if multiple applications need to access the same database, then this implicit schema can lead to inconsistencies and misunderstandings can happen. Right, so this is one of the challenge which is faced. So next we have is no central schema validations. So this is the first. Next I have is no central schema validation. So under no central schema validation, if you are looking at the relational database, there is a proper schema which is enforced and it has to be validated, and all the steps have to be followed. Whereas in case of schemaless database, it lacks the built-in validation. That is, there is no built-in validation. There is application has to manage. It has to manage the data integrity, consistency, and correctness. So the database cannot prevent different applications from storing or interpreting the same data differently. For example, if one application uses NAME for name, and if other application is using NAME or S names, if it is using, in that case same thing you are storing, but then the names have the way you are storing is different here, right? So this inconsistency can lead to issues where different applications will interact with the same data. So thereby again this is a challenge. Next we have is difficulty in difficulty in understanding the data. Because there is no explicit schema, it becomes difficult for us to understand. So in order to understand the data, I have to look into the application code. We have seen it is hard coded here, right? So it is time consuming. There could be errors when I'm trying to understand, and I should have the deep knowledge of application code. Next I have is increased complexity in multi application environment. That is, if the same database is being accessed by multiple applications, so schema consistency becomes a problem here. That is, these applications will make different assumptions about how the data is stored, and thereby there could be compatibility issues which can come up, right? So we have a few strategies to overcome this. One is the encapsulation and we have delineation. So in encapsulation, I'm limiting the database interactions to a single application. I'm using the web services to interact with others. I'm encapsulating the database. Next I have is delineation. So here I'm clearly defining different areas of a aggregate for different applications. Like there will be separate sections in a document or different column families. So by using these, I can overcome the problems here or mitigate the issues of this particular increased complexity in multi-application environment. So this was about the challenges and problems of schemaless. If they ask about schemaless, then do mention these and what are the key features of schemaless, explain all these, and then challenges also you can define it here. Next we have is materialized views. Materialized views is a tiny topic. So view in a relational database is a virtual table which we are creating, right? So this virtual table is derived from the original table. So you are right, you want only 3 columns of our original table. So you'll create a view and store it separately. It is stored in the virtual memory. It is not actually stored, but then once that transaction is done, once that interaction is ended, that table would be deleted, right? So here we don't store the data itself, but instead we compute the data dynamically when we want it. We are writing query to do that, right? So by these views, it helps us to get the customized view of the data which we want, right? So, but one drawback is these views are very expensive. They are computationally expensive, especially when we involve complex queries and large data sets. To overcome this problem only, we'll come up with the materialized views. So materialized views, yeah, so I have mentioned the same thing here. Materialized views are pre-computed cached views stored on the disk, useful for heavy queries that can tolerate some staleness. That is, materialized views are having a pre-computed view which will store the results of query physically, which is typically on a disk. So it's like a regular view only, but instead of computing the results on the fly, the results are cached and stored. Thereby, if you're storing it, accessing it also will be fast, right? So if you're not changing the data, or if you're not switching off the data, if you're switching off the system or the transaction, in such situations, the queries results need to be accessed regularly or more often, right? Thereby you can come up with the materialized views. So they are ideal for scenarios where you need quick access to computed or aggregated data, but you can tolerate the fact that data may not be up to date all the time here. So under this we have two strategies. So the first one is eager updates. So eager updates means materialized views are updated immediately when you update the data. When you update the actual data, here it has to update immediately. So this is ideal for, let's say, stock market. So in stocks, the data gets updated every now and then, right? In such cases, we can go with the eager updates. In batch updates, materialized views are updated periodically. For example, the internal marks which are updated periodically, right? So thereby it is not necessary to update every now and then. So once all the 3 internals are done, you can update them accordingly, right? So thereby you are reducing the overhead of time updates, real time updates. If you are speaking about how to create the materialized views, they can be created or they can be built outside the table, outside the database. So but often database supporting creating them directly with the computations and parameters. So materialized views can be stored within the same aggregate. That is, order summary should be there inside the order document only, right? Thereby it will also improve the query efficiency. If you are speaking about the column family databases, then you commonly use a separate column families for materialized views, and you are allowing the atomic updates to happen. Speaking from the efficiency perspective, if you are making use of materialized views, then efficiency will be higher definitely. Next we have is modeling for data access. So this is the final topic which we have. So when modeling data aggregates, we need to consider how the data is going to be read, as well as what are the side effects on the data related to those aggregates. So here we have summary about the figures which are given below. So the first one is key value stores. So key value stores should be used, or it is ideal for fast access to embedded data, but it requires passing on the client side. Next we have real-time analytics. So real-time analytics will involve denormalization, and it will have real-time updates to aggregate the supporting business intelligence. Then we have document stores. So document stores will support flexibility with the querying inside the document and maintaining separate objects. For example, maintaining separate objects for customer and order. Next, speaking about graph database, modeling relationships between different data points with easy traversal related to and related query operations can happen here properly. Speaking about the column family, it is optimized read performance by storing related data in ordered column and families. So for the given figures, these are the summary or the brief explanation which I have given. So the first figure which we have is figure 3.2. So this figure is embed all the objects for customers and their orders. So here we are making use of key value stores where customer and order details are stored together, right? All data is retrieved in one go if you want, but this requires parsing from the client side. So because to read the data, suppose let's say orders or products sold in each order, the entire object must be read and parsed from the client side. So this is about the key value store. Next we have is figure 3.3. This is about the denormalization for real-time analytics. So here aggregates can be updated to include the related data like order containing a specific product and all. So this technique is useful for, or it supports the real-time business intelligence BI, and it will allow the business analysts to gather the analytics immediately. So whenever an order has been placed, immediately the data has to be updated here, right? So thereby the denormalization process actually works properly for the real-time analytics here. So orders by product are stored as references here, thereby linking to their associated orders are happening here properly. So here is the JSON format representation which we have written for the orders as well as for the other details here, right? So if you can see, order payment is being written separately here. Next I have is figure 3.4, which is about column family stores. So column family will store the data in ordered columns. So this is for one column and this is for another column. So here we have the customer info and orders, order details, product and payment are stored separately, right? So this model is based on the query requirements and they'll ensure easy access. So here denormalization can be useful for the performance. So here there are different column family stores like customer order for different purposes, right? So this customer family holds a reference to all the orders that we have ordered here, right? And thereby it will optimize the performance the performance of getting the details, right? Next, the last figure which we have is graph database model. So in graph, objects are modeled as nodes. So order, payment, address, customer, all these are nodes, and the relationship is written in the edges form. So here relationships can be named as, and they have directions also. So product is a part of order. So but order is not a part of product, right? So it is one way, unidirectional. All those things have been specified here. By specifying all these things, it becomes easy for us to retrieve the data, retrieve all the customers which are linked to a particular product or any other details which I want. So this is a very efficient for use cases like recommendations or finding patterns, social media, social networking and all those things. So yeah, this is about the modeling for data access. So in exam, this could be asked for 10 marks, and for 10 marks also they'll ask either any two or three of these. So either key stores could be asked, document database could be asked, and column stores could be asked. So for that you should write this, explain this, what is key value store, and then you should draw this, what is column family, and then you should draw this and explain what is graph database firstly, and then how graph databases you being used here. So this was about first module. Stay tuned. I'll be uploading the other modules pretty soon. If you have any doubts, do let me know in the comments and subscribe to my channel. Thank you.